Hi everyone, so today we're looking at section 3.2, which is about simplifying expressions with radical exponents. And all that means is that your exponents are fractions. So we've talked about a little bit how fractional exponents represent various roots of numbers. Instead of just using square roots, we're also using cubed roots, fourth roots, fifth roots, etc., right? And how we can simplify and rewrite different notation of radicals and also exponent numbers. So your warm-up exercise, simplify the expression 4 to the third power times 4 to the eighth power. We're just going to find the sum of those two exponents. 3 plus 8 is obviously 11. And then number 2, 8 to the fifth over 8 to the negative fourth. Because this is a negative power, this whole term goes above the fraction bar into the numerator, which just leaves us with a 1 in our fraction bar, and an 8 to the fifth and an 8 to the fourth in my numerator, which simplifies as an 8 to the ninth power. Again, simplifying radicals, for the square root of 48, I can pull out a factor of 16. So 16 times 3 equals 48. When I find the square root of 16, it's equal to 4, and I'm left with the square root of 3. Square root of 30 times the square root of 15, I can either multiply them together to get a larger number and then find the square root, or I can do them in parts. It looks like 30 times 15 is 450. Square root of 450, and if I can pull out a number, so seeing the 15 on the outside, square root of 450 is the same as square root of 225 times 2, and I know that 225 is a perfect square for the number 15, so I pull out that 15, and I'm left with the radical 2, just like given in the answer below. Looking at some examples of various expressions, example 1 says use the properties of rational exponents to simplify the expression. So again, using my product rule, I'm going to say 7 to the 1/4 times 7 to the 1/2 is the same as 7 to the 3/4 power, because that's 1/4 plus 1/2. 6 to the 1/2 times 4 to the 1/3, and then quantity squared. I need to multiply the exponent terms, so I've got 6 to the 2/2 times 4 to the 2/3, and then I can add those exponents. So 6 times 4 is 24. 2/2 plus 2/3 is going to give me, this is actually a 1, right? So it's going to give me 5/3 total. Letter C, 4/5 times 3/5, and then raised to the negative 1/5 power. I can combine my terms here, so 4 times 3 is going to give me 12/5, and then that raised to the negative 1/5 means it all has to go in the denominator. So 1/12 to the 5th power, and then to the 1/5 power. Well, when I multiply 1/12, that gives me 5/5 or 1. So I just have 1/12. 5/5 to the 1/3 power is the same as 5 to the 1/5 to the 1/3. So I can subtract here and just simplify using the quotient rule. So 1 minus 1/3 is 2/3, so 5 to the 2/3. In letter E, 42 to the 1/3 power over 6 to the 1/3 power, and then all squared. 6 is a factor of 42. So 42 divided by 6 is 7 to the 1/3 power, and then squared. So that's 7 to the 2/3 power. All we're doing is utilizing the rules that were given to you in the note sheet from class. So make sure that you're following along and that you're identifying the rules as we go so that this gets easier and easier. Also, you want to make sure that your exponent notation is really specific and that you are, in fact, writing powers when they're supposed to be powers, and you're writing them in the right size compared to your whole numbers so that we don't get confused. Example 3, we skipped example 2. Example 3 says use the properties of radicals to simplify the expression. So again, the cubed root of 12 times the cubed root of 18. Because these both have the same roots, I can multiply those two base numbers, 12 times 18, to get a larger cubed root. And the reason I'm going to do that is because 12 is not a perfect cube and 18 is not a perfect cube. So the two of those numbers individually are not going to help me, but when I put them together, they might. So 12 times 18 is 216, and the cubed root of 216, if I think to myself, well, is that a perfect cube? I can think, well, maybe in terms of the number 5, because the number 5, I know cubed will actually be equal to 125, which is somewhat close to 216. So I can see if maybe the cubed root of 216 would be 6. So 6 times 6 is 36. Times 6 would give me 200 and, oops, a little off here. 216, right? So the cubed root of 216 is equal to 6. Letter B, same kind of thing here. I've got the fourth root of 80 and the fourth root of 5. Now I can break that 80 up into different components to make that work for me. So basically, because 5 is a factor of 80, I'm going to see if I can rewrite that in such a way. So 80 divided by 5 is actually 16. So I've got the fourth root of 16 times 5 over the fourth root of 5. And that's helpful because the fourth root of 16 is actually 2, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So I can pull out that 2 and have it times the fourth root of 5 over the fourth root of 5. Now, when I have a quantity over itself, it's equal to 1. So the fourth root of 5 over the fourth root of 5 is equal to 1, which is just left with an answer of 2. Some of the stuff that we're using when we're simplifying are identity properties, commutative, associative, right? These are things that we learned way back in middle school, like the fourth root of 5 over the fourth root of 5 is actually equal to 1. You know, when you have those things in your brain, these problems come out much simpler. Write the expression in simplest form. The cubed root of 135. Well, 135 is not a perfect cube because I know that 5 times 5 times 5 is 125, and that gets really close to 135. We just did the perfect cube for 6, which is 216. So we don't have a perfect cube here. We need to factor one out. So I can think about the perfect cubes that I know. The perfect cube for 2 times 2 times 2 is 8. For 3, it's 27. For 4 times 4 is 8, times 4 is 32, times 4 is 128. For 5, it's 225, right? And so I could keep going. But when I'm looking for a perfect cube, I'm just trying to see if it's factorable. So 135 has to have a factor here that will work. So 135 divided by 3. I'm sorry, 135 divided by 27 Ooh, that worked. So the cubed root of 135, when I divide it by 27, I have a factor pair of 5. So 27 times 5 gives me 135. That's why I'm rewriting this. So this is the same as the cubed root of 27 times the cubed root of 5. Now the cubed root of 27 I know is 3. So 3 times the cubed root of 5 is going to be my answer in simplest form. Moving on to example 4, the fifth root of 7 over the fifth root of 8. So the directions here say make the denominator a perfect fifth power. So because I already have the 8, I'm going to say that it's going to be 2 times 2 times 2. That's equal to 8. So if I multiply it by another 2 times 2, which is 4, that will give me 5 2's, which is a perfect fifth. So 5 to the square, the fifth root of 7 over the fifth root of 8 times, basically what I need here is the fifth root of 4. Now I can do this because the fifth root of 4 over the fifth root of 4 is just 1, right? It's an identity. So even though I'm going to be changing the value of my problem, I'm changing the way the numbers are written. I'm not changing the value, right? I'm still multiplying by a 1, so I'm okay here. So the fifth root of 7 times the fifth root of 4 is the fifth root of 28 over the fifth root of 8 times the fifth root of 4 is the fifth root of 32. Now the fifth root of 32 is equal to 2. There is no fifth root of 28, so that's the simplest form I can put my equation in. Example 5 says simplify the expression the fourth root of 10 plus 7 times the fourth root of 10. Well, I have 1 fourth root of 10 and 7 fourth roots of 10, so that's going to equal 8 fourth roots of 10. Same thing here. I have 2 times the 8 to the 1/5 plus 10 times 8 to the 1/5. That's going to give me 12 times 8 to the 1/5. And remember, that notation is the same as 12 to the fifth root of 8. Okay, I put a couple of problems here for your daily homework quiz just so that you can practice and keep working on these problems. We're going to finish working on these throughout the rest of the week, so hopefully this video gave you some extra practice.